Howdy, everybody. Did we all just get trolled today? Like, this was a crazy one. Um, I'm here for day 20 of Advent of Code, and I honestly, for part two, feel like I got trolled. So, uh, let's just, oh, I forgot here. Hold on a second. Let's just talk about the day and see what happens. I'm going to pop up a thing so I can draw stuff, but I don't even know why I'm drawing stuff for part one because honestly, part two, man, really got me. It is funny. It's a lesson in please remember to look at the input um and see what's going on. But okay, let's just start with it and talk about it. Okay, it's called race condition. We have another graph, but again, the graph trolled us. So what is the idea is you're doing a race from start to end. You're still in a computer and it's like you're racing um other programs to get to like the end in the fewest picoseconds is what they call it, but it really doesn't matter. It's still just a graph going from start to end, and your goal is to find the shortest path, right? So we've all seen this before. It's like Dijkstra's or some kind of breadth first, probably breadth first search or whatever. In this case, a depth first search would have been great. But the idea is you're just trying to find the shortest path. And so you start here and you make your way to the end, and then it has a bit of a gotcha to it. It basically says, but you're allowed to cheat. And the cheat is you're allowed to jump over a single wall. And the way it's described took me a little second to understand, but exactly one time you can cheat for 2 picoseconds, which means is you can pass through a wall. So the idea is like if you're going down here, you could like cheat across this wall for 2 seconds because you're right here, you're in the wall for 1, and then you're out in 2, so you're safe, right? That's the 2-second rule. Is like, can you just get across the wall? What it means is you can't do like double or triple walls. Like you couldn't cross this area right here, but you could cross any of these areas right here, right? These would all be fine to cross. And it allows you to cheat, right? Because I think if you go from here to here, you've now skipped this whole section. And what it does is it says, well, if you go through your whole path, you can actually find a bunch of cheats. Like, for example, look, this, you can actually cheat from this position to the end. And so if you enumerate all the cheats you can do, they say, like, for this test example, there's 14 that save you 2, 14 that save you 4, and so on and so forth, right? There's a bunch. And this last one that saves you 64 is the one right here that allows you to jump, and that saves you the most. And then so what the question is like, how many cheats can you do that would save you at least 100 picoseconds for part one? So the idea is find all the cheats, find how much time it saves you, and then if it saves you more than 100, you count it. If it doesn't, don't count it. So when I started doing this, my thought was to use Dijkstra's, and the thing that was going through my mind is like, once you've like built the path to get there, right? Like, let's say this is the shortest path from the 2 points. I realize that doesn't look like the graph anymore because you can't go in diagonals, but say this is the beginning and the end. You could just follow this path, and just for each point on the path, ask yourself if you can cheat to here or here, and if you can, does that like get you a new shortest path? Right? And then you can say, oh, so this new path takes you, 5 picoseconds, but the original took you 212. So now you've saved yourself 207 picoseconds. Right? So this one saves you 207 picoseconds. So that one's definitely the fastest, right? And my thinking was, so you say, oh, this is, so essentially you're saying, can I at this point find any cheats, and then I can do another Dijkstra's algorithm from this point to get that distance and sum it with this distance plus the cheat, right? So you can think about this new distance is Dijkstra from the cheat to the end, and then we want to add to that the cheat, which is 2, plus the dist from start to cheat, right? So we really just need to track this value right here plus the cheat. I could do this in a different color. I realize the whiteboards have different colors. I don't know why I haven't been using them before. So like the idea is we just need to track this distance and then the cheat, which is 2, and then this distance, which is the new Dijkstra. And the thought occurred to me is like, but that, what if that's the map's really big, and it actually is really big? Like if you look at the input, it doesn't look great like this. Let's see. Like if you look at the input like this, it actually is relatively big. So my thought was, do you really want to run Dijkstra every single time? So I prematurely optimized it, and I said, well, what if I keep a cache of all the known distances? Which is actually, I didn't re-implement Dijkstras this way, but Dijkstras will do that for you, right? Is you can actually do like a breadth first search and find all the distances to all the paths, because you get that dist thing, and then you can just kind of walk back and find the distances relatively easy. But the point was, is I said, oh, what if I do a cache? Because, for example, like, what if the cheat right here, so I ask, what's the cheat at this point? It takes you to right here, like this is the cheat. Well, I already calculated this distance, so I know what it is. So, and I know that I've gone this far down the path. So now I just, I can get this from the cache. I already know what this is, and I just add the cheat to it. And I don't have to run Dijkstras again. That was the goal, is like cache equals no, that was a G. No Dijkstras again. That was my hope, is like, oh, I can do this. So just to be clear, again, at a high level, the algorithm that I was going through my mind for part 1 was just find the original path, find the shortest path, and then traverse that path and see if I can find any cheats along the path, because the cheats are relatively limited, right? I can only jump 2 spaces. See if I can find a cheat. And if I can, what is the distance from the cheat to the end? And then I just sum all those up, and any of them that save me more than 100, I should count, okay? So here's what that code looks like. And again, it's pointless. I made a point. It's not pointless, but it's hilarious for part 2. I make a point, and I have some options for it. I say, obviously, I can create a new one. I want to know what my neighbors are. This is for Dijkstra's algorithm, so I can find the neighbors. And then I want to know what my neighbors' neighbors are. And this is probably badly worded, but I want to know, like, if I go in the left or in the west direction or whatever, what values are not only 1 position away, but 2 positions away. And that will allow me to check if I can cheat, right? I'll have those 2 values, and the one next to me should be a wall, and the one after that should not be a wall. And that's what gives me, and that's what you'll see that in a second. But so basically what this neighbors does is just gives me the next 2 positions in the same direction. We'll do the distance for part 2. But then I just create my map again, right? So I have my nodes, I have my start and end points. And I just did the 4 loops to iterate through them. I create a new point. If I get a dot, I insert it. If I have an S, I know where my start is. If I have an E, I know where my end is, okay? And then here's my neighbors function, where I say, okay, go find all the neighbors of the point, filter it by the ones that have nodes, and then add the size to it so I can do Dijkstra's algorithm, just to collect those. The cheats is pretty similar, right? Except instead I still get my neighbors, but I call neighbors. So now I have the 2 points, and I just say the point closest needs to be how do I say this? The point 0 is the second one away. So this is where it's probably like badly worded or badly described, but the one furthest away needs to be a node, but the one closest should not be a node. So the idea is what Maybe I can describe this a little bit. The neighbors function gives me 2 points, like so P0 and P1. And so say this is my X here, my current position, and this is P0 and P1. So we're going this way. This one should be a wall, right? I shouldn't be able to get there. But then this one should be open, right? So, and that is what is akin to a jump in this case, right? So I can cheat and jump over this to get to this. If it was anything else, I couldn't do it, right? So this and this is a no-no. This and this doesn't really help you any, right? Because you could have just traversed this, so you're not really cheating in that sense. So that's what I do is I still go through my neighbors, but instead of just checking to see if they're in the nodes, I say, hey, is the farthest one of the two in my node list and the other one not. And that allows me to get the ones that I cheat. So what do? I just run Dijkstra's, and this time I decided to use the pathfinding library, which we've talked about before. We've already implemented Dijkstra's at least twice in this year. So I thought I'll just use the Dijkstra's that they give me. So I just need the successors function and the success function and then the start position. So you can see my set successors is just give me the neighbors, and the success function is, give me if the point is the end, I've reached it, okay? So I just run Dijkstra's, and now I want to keep that cache like I had mentioned. So how do I do that? Well, if you think about it, I now, this Dijkstra for the Pathfinder actually returns the path that you take. So it returns like the shortest path that you took. So I just take that path, I reverse it, enumerate it, and then collect those into a hash map, and that will give me the all of the distances, right? Because I'm doing it in reverse, maybe the way to visualize it is because I'm doing it in reverse, right here, the E would have a distance of 0. This will have a distance of 1, 2, 3, 4, 5, 6, and so on, if that makes sense. And so now I have this like cache. The idea being if I ever see a distance again, or if I ever see that point again, I can check my distances and I don't have to retest, if that makes sense. So what do? I'm going to keep track of all the cheats. And this is probably not the most efficient way to do it, but I kind of ran out of time in optimizing. This will be a day that will definitely be fun to go back to because part 2 actually changes part 1, which we'll talk about in a second. And then I just enumerate through the whole path, right? So here's my complete path. I'm just going to go through the path, and I'm going to ask how many cheats can I do, right? I was calling it jumps, but they're cheats, so I actually should change this right here. So I'm going to go through all the cheats that I can do at that point in the path. And if I've seen it before, and it's cheaper if it's a cheaper way to get there, I'm going to add that to my cheats list. Otherwise, I'm going to run Dijkstra's on it, right? And then I'm going to see is this new Dijkstra's path greater than my original path? And if it is, then it's not helpful to me anyway, right? Otherwise, I know it's gotten me somewhere, and so I add it to my cheat list, and then I add the new set of paths that I found to my distances, right? The thinking is like for that is, so say the cheat was to right here and the new path that like goes like this. I should add all of these distances now to the list, right? So if I'm cheating from here to here, if I add all these new distances to the list, then I have some kind of path that or I have how do I say this? I've updated my cache is probably the way to think about it, right? So what this is saying is, oh, I found some path that cheats that's better than my original, and so I should just add that to my list, okay? Or I should add that to my cache. Otherwise, if there's no path found, right? Like maybe this path took me into a place that like gets me hard stuck and there is no additional path, right? So I might get a none here and I should just ignore it. So now at this point, I've collected all of my cheats, right? These are all the ways that I've cheated and the cost to get to them. And so now for part one, I can just say, hey, for all my cheats, filter by where the difference between the original cost and my new cost is greater than 100 and count those up. And that gives me part one. Now, this could definitely be optimized. Again, I say I stopped here kind of because the reality is we're just counting. So there's actually the potential for you to do this in kind of like as opposed to like keeping a list of cheats, just keep a count of the number of cheats that would do it. I think the reason I originally did this is because in part one, it was easier for me to visualize, right? So like he gives you you get a list right here, right? So you get a list that says here's all the cheats. And so I was originally using it as a vector. You could definitely say, and maybe before I put it in the gist, or maybe as we go further, we'll simplify this even more. In fact, I'm not even sure. We'll look about it. It might be fun just to try and do part one and part two at the same time. And so we'll try that. Anyway, so that's part one. You again, the general algorithm that was going through my mind for part one was go through the original path and see if I can find a cheat. And if I can, update my cache and then track those cheats. And eventually I get to some better, I get some list of cheats. And then I just say to myself, okay, which of them save me more than 100, more than or equal to 100, and count all those up. And that gives me part one. So this is my answer for part one. You can see, even though it's like, how do I say this? Even though it's like a pretty big map, it runs really fast in 4 milliseconds. And that probably should have also been an indicator of what's going on. So anyway, with that, let's move to part two and see why I think I got trolled. So what does it say this time? It says, all the programs think you're an idiot because the cheats can last up to 20 picoseconds now. Not so the idea is the cheat is no longer 2 picoseconds, it's 20, meaning you can do these huge jumps now, right? You can just like literally do like a blah and go through a whole bunch of spaces to get there faster, right? So you can go from here literally to here, and then the end is only like a couple things away. So you can now get there in like a distance of 8, because you can actually jump through these 6 things, right? And the same thing right here. It mentions though that like this is the same cheat because the start and the end are in the same position. And that's a little bit of a hint, is like you say to yourself, okay, well, my cheats only work if the start and the end are different. And so if I've already found it before, I don't need to find it again. And that's the only thing that changes. It now says if you can cheat for 20 seconds or 20 picoseconds, how many cheats save you at least 100 picoseconds? So now the difference is 20, but the question is like, does that help you, right? So I started thinking about this and I was like, wow, how does that even work? Because like the thinking that was going through my head is, notice that this one like curves around. So there's a potential for the cheat to be like the way to think about it is your cheat could do like anything along the Manhattan distance that gets you like closer to the end. And like that's what was going through my mind, is there's some like you'd probably never snake back or anything like that. Like you'd never go to right here. But then I was like, actually, that's not the case. Like, what if these are all blocked up, but you go right here, and then the end allows you to like go down here. But then I was like, well, what does that mean blocked up? That would only happen if you were like, if this was number 19 and then this was 20, so it saved you. Like if you could still go down here, you would. All of that is to say, I was trying to figure out how to do this part two. And I thought I should kind of print the map or look at the map and see what it looks like. And I'll show you. It's probably easier to look at it in here. So here's the original input. And you can see it looks like it's going all over the place. And when I'm first visualizing it, I'm like, okay, that's a little crazy. And I see let's see, you can see the start, at least for mine, right here and right here. And so I'm like, okay, there's definitely like these paths where you can kind of go like here, and then does that get you closer to the path? So I started tracing it, and I was like, oh, that's kind of weird. But there's definitely, it feels like there's paths that can just get you here. So you definitely are going to like have to move through a bunch of these. And then the thinking that was going through my mind is like, well, can you just cross paths? Like, say, because you're trying to find all of them that save you 100, right? So the question is like from going from here, this one right here, you can go to right here to get you close to the end, right? Or like this one, you can go to like right here, and that gets you really close. You can actually go to right here, right? Because you can go up like this, and that gets you really close to the end. And presumably, you can see it starts to. Anyway, as I'm doing this, I start noticing, where are all of the intersections in this thing? I'm not seeing a lot of intersections. And so I was like, okay, I'm going to print out, not only am I going to, so here's my input. I said, I'm going to print out my shortest path so I can see what it looks like. And here it is. This is the shortest path. And if you look, you will notice that the shortest path is completely filled in. You go from start to end, and there are literally no dots throughout the entire thing. Not a single dot. I did print it out wrong because I have 2 extra here and 2 extra here, but you can ignore that. It's not. The point is, the point is, going from start to end, you literally fill every single dot. There are actually 0 intersections. And I verified that by looking at what is my path length and what is my node length, and they're the same, right? And then the duh moment is, okay, well, that's why it only took 4 milliseconds to do Dijkstra's, because literally all you're doing is just traversing a single path. That there's no decision making in this process. You literally are just going from start to end. So every point on the path is a point to the end. Okay, so how does that hint help you solve part 2? Well, if you know that every point is on the path, the only question you have to ask yourself is, does going from one point to the other take less than 20 steps to get there, or less than or equal to 20 steps to get there? And are those 2 points on the path far enough between each other that you would save 100 steps, right? So what do I mean by that? It may be a little confusing. Let's see. So we know the path is winding. We'll kind of stop. We'll do like a weird lazy winding like this. And so here we'll say this is the end and this is the start. So we know that it's doing this winding thing, and every point on the path, how do I say this? You can ask yourself from the start, is there a, how do I say this? If you're at the start, how many points on the path would get you to plus 100 picoseconds? And the answer is, the only way that would happen is if it was more than 100 steps away, right? So it only helps you if you're more than 100 steps away, plus the 20 it takes you to get there. And so you actually, the way to think about it is you only have to consult when you're at any position in the map. You actually only have to look at all of the nodes that come after it, right? So there's no reason for you to like jump back to this node. Like this way is bad because it makes it worse. You always want to jump forward, right? And how far should you try and jump forward? Well, you should try and jump forward enough that it nets you, like the net is greater than or equal to 100, right? So if you only jump one position forward, so say you're consulting this and you jump this, and the distance between these is 1, well, you've only saved yourself 1 second, right? Or 1 picosecond. So you definitely want to go far down the list. But you also, it's notice how the thing is winding around and it winds all over the place. You should ask yourself, like, what is the distance from here to here? Well, the distance from here to here may only be like 5, right? So you go like 1, 2, 3, 4, 5, right? So the distance between those two is 5, but let's say that saves you, 500 steps or whatever, right? So now you know that one is definitely better. I hope I'm describing this okay, that you guys understand that. But the gist of it is, I don't have to do anything crazy. I don't even have to do like just check all the nodes, compare them to the other nodes or anything like that. You can literally just say, well, I know literally every single thing on my path, and I know their distance to the end. So I just have to ask myself, does the difference between these two distances net me 100 in the path? And also, is their distance like close enough that I can jump to them without getting in trouble, if that makes sense? So what does that look like in code? And hopefully this will make more sense when we look at it in code. But it made part 2 feel like an actual troll. I felt trolled. So here's what I do. I'm going to create a new distances, but I'm, instead of using a hash map to store it as a cache, I'm just going to store it as a vector. So now I have my distances from the beginning to the end. And I'm going to iterate over all of those distances. Notice here I use parbridge. This was a cool tool I found that allows you to... do I even need to use it here? Can I just do par iter here? I don't know why I couldn't do it right here, but you can use parbridge. Basically what it does is it turns any iterator into a parallel iterator. And I don't remember why I had to do that. It may have been I was doing it a different way. But I'm doing this in parallel, is what I'm saying. I'm using Rayon. And I just say to myself, hey, for each of my distances, or for each of my points, consult all of the other points on the list, but skip up to that point, right? I don't need to check anything behind me. And then I'm just going to ask myself the question, for those 2 points, is their distance less than or equal to 20? And is the difference between their costs minus the distance greater than or equal to 100, right? So this is literally just saying, like, is the distance between the 2 points within the valid cheat distance, and it does the cheat net me more than 100? Does the cheat net me at least 100 picoseconds? Like, this is literally what I'm just asking myself here. Is the cheat valid, and does the cheat net me 100 points? And then I can count those. And so for each 2 points, I just say how many of, or for each point, I ask all the other points below me in the map, or sorry, in the path. I say for all the other points below me in the path, does it is the distance between this point and that point a valid distance, and does it net me at least 100 picoseconds? And if it does, I count it up. And I just do that for literally every single point, and then I sum up those, and that gives me part 2, which is this. And you'll notice part 2 finishes like just as fast as part 1. And why is that? Is because I have some set of distances n, and I'm only consulting on average half the distances. So it's like n times n over 2, right? I'm only consulting like half the distances for each of them. On average is what I do, right? Because the last one, I only consult a few, right? A couple. And then, somewhere in the middle, I consult about half of them. But I can basically skip, right? I can skip and say, hey, does this net me something? Oh, no. I can skip because I know I don't need to do anything before me, right? Is the way to think about it. Um, so again, at a high level, what am I doing in point two? Is I'm just literally going through all of the points, and I say for each of the points after me, is their distance um, within 20, right? Is it less than or equal to 20? And does it net me 100 picoseconds? And if both of those are the case, then I know that it's a win, right? And that gives me the answer for point two. So why does this feel like trolling? Is like if you had looked at the map, it it would be painfully obvious. And if you hadn't looked at the map, which is where I was going, you're creating this convoluted way of like basically you're taking part one. And I should say I think you can actually still do it and get it to work. It's just if you look at the input, you feel like you got trolled, right? So what would you do in part two if you were still doing it this old way? Is you would say, does the how do I say this? You would instead of saying like where is it? For these cheats right here. Essentially, you would just say, "Hey, for these cheats, I'm now going to allow myself up to 20." And what that means is you would now create like this cheats 20 function, and it would basically go through all of the Manhattan distances in all of the directions, right? You imagine like you have a point right here and you would like go all of the Manhattan distances that are 20 away or within 20. So you'd have some block of distances and you'd basically just consult all of these points and say, are all of these points in this area going to net me something further? And I think that's where my caching would have helped a lot, is if I'm just caching these things, like how close do I get to find because I'm doing so I what should I say is because I'm doing so many of these, it feels like the likelihood of overlap is really high, and so having that cache would have helped a lot, right? Like just imagine you have like this grid and you have this point over here that's on your path. Well, your next path is right here, and so that let's see, maybe I do this in a different color. Your next path is right here, and its grid of overlaps is like, it's even worse. It's like this, right? Like that's the overlaps for this one, and that's the overlaps for this one. I didn't draw this right, but they very much overlap. And so there's no point in you, like, if you've already like done this work right here, there's no point in you doing that work again. Just do this stuff right here. And that's where the caching would have helped. So that's how you would, in my mind, if you hadn't looked at the map and seen it, maybe that's the way you alter part two, is you just say, okay, I'm going to create a cheats 20 that like does a fan out of like, what are all the points that allow me to cheat 20 that get me to a valid spot, and then just do the same thing, right, over and over again. But when you look at it, you actually don't have to do that. And so I actually, for part of this, what I'd like to do is I still want to look at some advent to code solutions and see how many people found the troll or whatever. But I'd like to do part one and part two using this this new way, because all that really changes is this distance map, right? Or all that really should change is we just say, hey, what the distance has to be exactly 2. Is the distance 2? And then otherwise nothing changes here. So I kind of want to consult this and see if I can get both of the distances. I'm trying to think if I can do this in a functional way. So it would probably look something like this. Let's see. I still do this. I'd still do this. I still do this. But I think I'm going to fold now. So I do a because I want to keep track of both of them. So I do a fold of 0 and 0. And then I have my accumulator do. Let's see. So I definitely have this. So now I have my accumulator. And so I would say, like, I still want to track both the distances. But I say, well, okay, let's just, if this is less than 20 and this, so this is the part 2 case. So I would say act.1 is this. But then I would also have an if distance equals 2 and it nets me this one. I don't think I need an else if, though, because I want to test both cases. So it's going to look like that, and then I just return the accumulator. What doesn't it like? Oh, it's not fold, huh? No, it is fold. What am I missing here? Oh, it's because I'm. Is it because I need to do like this? Oh, I'm missing this. Takes. Oh, so can I actually can do this then? Maybe doing this live is always scary. Where did I go? So we wanted to look like that. Okay, is that it? So now we have our two distances, and so to map them, we want to like reduce these. Okay, yeah, it's already figured it out for me. And so now we can say print line. Oh, we can pull them out here too. We can say P1, P2. I mean, these elapsed times are going to be hilarious because they don't matter. But I think that will give me the right answer. Let's try it. It actually doesn't. Oh, and it actually makes this wrong. Okay, so is my counting wrong? If the distance is 2 and d2 minus d1 is greater than equal to 100, do that one. If the distance is less than or equal to 20 and d2 minus d1 is greater than or equal to 100. Increment this accumulator and then return it. And so now I've folded these into 2 pointers and I reduce them by just summing the first with the second. Okay, maybe I can't put these together? I don't know. I'm almost sure you could. What am I doing wrong here? Oh, minus distance. Is that what I'm missing? Sometimes I feel like the AI doesn't actually help you, right? Okay, there you go. That gives me the right answers. Okay, so this does actually do it. So you can literally get rid of all of this. Oh, I do need the... that. But there you go. Oh, maybe I include Dijkstra's in this. But you don't even need Dijkstra's in this thing, right? So there you go. Okay, so this is it summed up, right? Because why does that work for part 1 as well? Well, if it's a single path all the way through the thing, though all that you're doing, the difference between part 1 and part 2 is part 1 is you have to jump exactly once, so the distance has to be equal to 2. And then for part 2, you can jump up to 20, so the distance has to be less than or equal to 20. So how does that change? It used to be that I was just iterating over it. Now I can do a fold and keep track of both of them at the same time, and then I can reduce at the end to get both parts 1 and part 2. Okay, so if I haven't expressed it enough of how much a troll this feels like, it was a little hilarious, right? You don't even need half of this stuff. I think I'm going to keep it around just for giggles, so you can look at both things. So you can see kind of how I did it both ways. And you can see that, it's not really crazy. But anyway, I found it totally hilarious that if you look at the input and then you look at your output and you see this, you're all like, oh, okay, that greatly simplifies the solution. Is it a generalized solution? Probably not. And if I had more time, I'm already running out of time. Like the thing that I think, again, like I think the way you would do it is you'd have this cheats 20, or you'd modify this cheats to be a cheats 20, where you like spread out and look for all the potential cheats that you could go up to 20 in a space, and then go through all those points and do the same thing. And that's where this cache would be really helpful, right? Is if you've already seen it before, you can increment that thing pretty easily, right? You'd have no problem getting to those. Anyway, there you go. There's day 2. Let's go see how people solve some of this stuff. Right here. Oh, I don't have it up. Okay, let's see. Oh, this guy is visualizing, or this person's visualizing all the cheats. Yeah. You can see there's actually quite a few cheats that you can do throughout the thing, especially on the input case. Haha, I can't read. Day 20. Today was 99% reading comprehension one. Why is that the case? Was there something that I missed in the... Yeah, there's only one path to victory without cheating. That is the troll in my mind. There's only one. Cheating for 2 picoseconds meant you could jump over 2 walls. Yeah, that would mess you up. Yeah. And it did kind of troll you. I mean, it wasn't a troll, but the wording You had to be very strict on the wording to understand what was being said. It did change. Well, it never said 50 picoseconds in the test, did it? Oh, in part 2, it might have. Oh, here's the example with 50 or more. When I went to part 2, I guess I hadn't read it through enough yet because I was trying to figure out the thing that was I was trying to figure out at first was, okay, it looks like it's the same as part 1. I just have to from this position, what are all the valid plus 20 cheats? And I had to figure those out. And so that's what got me on this one, which was kind of hilarious. Yeah, this is what I was thinking is you could kind of do something like this as you're going through the path. That totally works for part 1. And my thinking for part 2 was, okay, now I'm going to do it for 20, right? I'm going to have this Manhattan distance thing like here that's going to say, okay, here's the thing that are 20 away, and I just have to find the valid ones that are at least 20. But keeping the cache, I think, would save you a ton. Because again, if you're only moving like one step up or one step up in the path, most of those are still within the same Manhattan distance. And so if you've already solved them, though you can figure out the count. Why? Manhattan distance. X2 minus X1 plus 1. Oh, okay. Absolute, you need to do the absolute of these two and then sum them, right? Is that what he's saying? Or they're saying? Yeah. Oh no. Yeah, these little bugs always get me. I don't know if you saw, but when I was trying to solve that, I was thinking the AI would just do it for me, figure out the AI. The AI would figure out that I'm just trying to copy these two, and it did not. Did it still not copy it down here? I must have reverted. Or undone. Sometimes the AI trolls you, right? And so part of me wonders, is the AI actually helping? I checked for dist greater than or equal to. Oh no, yeah. So honestly, those little bugs can really get you. Have you solved day 20 already? It's not going to be another 2D pathfinding grid puzzle, is it? Well, I would like to say though, in defense of advent of code, all of the grid puzzles have been different. Some of them have just been straight up. One was straight up Dijkstra, but they've all had enough like craziness to them, and you actually see this in previous years. Many of them do end up being graph pathfinding type things, but they're different enough that it feels okay, if that makes sense. Yeah, this is the thing that I was talking about for part 2 is like, if you didn't realize that you could just kind of test, you might do the same thing and just kind of walk through and find all of them and ask yourself, are those closer? It might be, I think that might be interesting to do that and see like how much it costs you time wise to do that, because it's possible that it's not like terrible and it's still an okay solution, if that makes sense. Okay, it looks like more people got part 2 with the 50 versus 100. It must have just been that I never actually had to, like, I was still trying to figure out the solution, and then once I figured out the solution, I was just like, oh, it's literally just, and so I must not have clamped on to using the test case for the part 50 for the 50 for the test example. I don't think I used the test example for part 2 because I was like, okay, well, if I just have 2 arrays in part, if I have a list, I can just go through that list, essentially was my thinking for part 2. What is this? All the shortcuts? Oh, is this like from this point, these are all the valid shortcuts? So for each point, it has the shortcuts that you take? Okay, that's a crazy visualization. Did I get trolled? I actually did not even pay attention. Does it actually say that? All this programs is idle. You just arrived in time. The race takes place for you. And a map of the racetrack puzzle for you. Start and end when. Because there is only a single path from the start to the end. Oh man. Oh, it's even worse. It is not reading. Me not reading. Wow. That would have totally been like a, oh, well, if there's a single path, I just literally traverse the path. And then my code would have actually just looked like this for both parts 1 and 2, right? Oh, man. Yeah, you don't even have to do Dijkstra's at all for this one, right? It is not a pathfinding algorithm at all. Like the path is the same. You're literally just it's really just math, right? You know how far each point is along the path, and then you ask yourself, can I jump from one point to the other? And if I can, does it net me enough to get me, to get me the plus 100? Oh man. I trolled myself. It wasn't him trolling us. It was I trolled myself. Okay, I trolled myself. I just keep using Dijkstra and it keeps working. Yeah, until that was my sentiment until this. Although that makes sense about the cheat thing. Oh man, I was not paying it. This bad boy can store so much state. Hash let's see. Yeah, yeah. Hash sets are cool though, right? It's okay to have a hash set. It's cool. Oh man, I feel like I trolled myself. Okay. That makes me want to look at the leaderboard. Because it feels like if you had read this, you probably get it really fast, right? Both parts in 3 minutes. I guess I don't know how many of these are. Yeah, you can implement Dijkstra's really fast. But there's we can go look at some solutions. It's quite possible that like some of them just saw it and were like, "Oh, I can just do a loop over the points as well as a loop over the other points." Let's see if we can find some people that got on the leaderboard. Use the taxi cab metrics. Okay, so like clearly this person noticed that there's only 2 points or there's only one path. And so yeah, you can literally just use taxi cab or Manhattan distance is what I always saw. So you're literally just comparing the paths. The distances, right? Okay, so I do feel like I'm trolling and I do I want to get rid of most of this stuff. How does it work if I do that? I still want to insert each of these into my nodes, but I don't have a neighbors anymore. And I don't have this. I don't even need to do Dijkstra's. So how do I create this new distances? I just start at the beginning. So I actually do want the neighbors ones, but I don't need this neighbors. And I don't need this cheats. Because what I'm going to do is I'm just going to say like, I think I can just say like that's probably not the right way to describe it, but I can say like let end equal map.end, and then while end does not equal start. Or I can just say let cur equal map.end. So we just do distances.push cur distance. And then we do let cur equals cur.neighbors. Can you not do a first? Oh, is it nth? Is that it? Why does it still not like this? Okay, there. Do you guys like upper or lowercase for your errors? Oh. I can't go backwards. That actually doesn't look right. The 1381 is right, but the other one's not. Right? 982 124. You start at the end. It's at, oh, holy cow, it's actually slower too. While cur does not equal map start. Distance is push. Curve is it insert cur. Cur is equal cur neighbors into inner filter. It exists and it's not in my visited list. Get the first one or exit. Distance plus equals 1. I mean, I guess I could still Dijkstra it. That's hilarious that it's not. Okay, that's right. Man, I feel so silly for not having found or seen that. Anyway, that's hilarious. It's literally part of the problem that says you don't have to do it. So, yeah, so what is the naive way is you literally just say to yourself, I'm just going to go through and try them all and see which ones. I wonder why that other way didn't work, but I mean, obviously Dijkstra's going to find it because the neighbors. I must have been just doing my visited wrong. Oh, I wasn't including my start, huh? Start has a bunch of them. Okay, let's try and do it. I feel like I'm running out of time here. I should be done, but I'm not. I'm just going to leave it with Dijkstra's. Okay, there you go. An actual crazy day. You can solve it super fast, potentially even faster than this. I don't know why. Oh, anyway, I don't know why I was having problems, but really not that hard to solve if you actually read the directions, because you can actually just ask yourself, is this distance within a jump range, and does it net me more than 100? And then you just add that to your list, right? And so you can do this really fast. So it really was. We saw a couple of those memes. Did you read the directions, right? And apparently the answer for me is no. Haha, I can't read day 20 instructions. Oh man, I totally feel that way. Okay, we're gonna go out on a high note. Let's see if we can't find someone's cool. Who got in like the leaderboard? Usually they put leaderboard or rank in their thing. Let's see if we can still find them. Because it'd be fun to see how quickly some of these people did their stuff. Yeah, my guess is everyone did this kind of the same way. Here's more like what I was thinking of doing in that second part, right? Is you basically just go through them and you add the distances. But you really, I mean, I think it's probably even simpler than that. Yeah, you can literally just do a vector and count over them. Way faster, way fast. Anyway, I got there on part 2. As part 1, I spent a lot of time finding a more generalized solution. That would be an interesting, like, quote unquote, part 3 for these, is like, what is your generalized solution? To get all the cheat locations for part 2, I used 2 generators. The second part was extremely slow. It was made worse since I was essentially checking something along the lines of dist is less than or equal to max cheat dist while passing 20 for the max cheat dist. Okay. So I think you could still do it this way if you didn't, like, for the very generalized solution. And again, solving it the easy way is perfect. But like for the generalized solution, I think what you actually do is you actually just traverse the shortest path and then go see if you can't see what the cheats are along those paths and see if that nets you anything. And you might have to run Dijkstra's again because the shortest path changes from that cheat path. Buy parts of the smart solution with the dumb way possible. I finally switched to just checking for Manhattan, but I'm too tired to see how I can't get rid of the n squared lookup I still currently have. Basically, I'm glad to be done, but ouch. Okay, we can look at it really quick. So he is doing a Dijkstra to find all the steps. And then for each of the points, yeah, he is checking to see. So for each of the points, he's checking all the other points. Okay, so that's where the n squared comes from. I mean, it's still like the idea is like I think what he's saying here is like for each point, check every other single point. So you're doing like a combination, like the math combination of the set of points over like k equals 2. That could be really large. Well, we know it's about 10,000. And so it's 10,000 squared, which is like, what is that? 100 million. So that is a lot from computing time, but if you parallelize it, that actually returns relatively fast. So you could do that, and I think that would actually be a valid solution. Like probably the way that you speed this up is you just use par iter. I don't see that he's doing par iter here, but you could use par iter in this part of it when you're like doing the double checks, and it probably gets you there faster. Yeah, because you are doing on the order of 100 million tests. But if you think about it, if you can do 10,000 parallelized with 10,000, that probably runs a lot faster, if that makes sense. Still a good solution, though. I mean, I think it counts. I'm going to give him a ding for it. Also because it's in Rust. Okay, I've spent enough time talking about it, and we reviewed some code, so I'm going to paste my solution. Anyway, I hope you had fun with the day. Apparently, I trolled myself, and I wasn't being trolled by the map. It is funny because I started with this as saying, "Oh, the map trolled me. If I just paid attention to the input, I would have been done." But apparently, it was right there in the puzzle, and if I paid attention, I would have solved it. Could have solved it even easier. So there you go. Hope you all had fun solving it. We'll talk to you tomorrow.